We said this before, but it cannot be said enough. Practice makes perfect. So how about we practice applying our laws some more? And maybe show off a little? Because you have gotten so good at them. Here's part 3 of our last example. What we are asked to prove seems to be a single step of multiplication, right? But remember that we need to prove it using the laws. Alright, our mathematical lawyer, let's first take the left hand side and bring it under the umbrella of solution. Right off the bat, we see some inverses here which we can isolate. Next, change the grouping of this expression through commutative and associative laws of multiplication. Now, simply rewrite this bracket like this, which you could also write this way. We pick the left side and reach to the right side, and thus our proof ends. Now, let's look at the golden rule of fractions in part 4. Starting from the left hand side, we multiply the fraction by 1. And recalling how inverses work, let's change 1 to k upon k, because it's initially the same. And there's our proof. Pretty straight and simple, right? Now we will try our hand at part 5, which is a rule with a nice long name. The rule for the quotient of fractions. If you focus on the left side, it looks like a mountain of numbers. But it's not too tough to sum it. Once again, we spy some inverses. Multiply the respective element BD to the numerator as well as the denominator. Next, rearrange the equation so that the inverses are placed together and they get cancelled. There you go. We have proved what we were supposed to do. Find out one final example before we close this section. It says something about the closure property. And we know, you are an expert on the closure property now. When it comes to addition, the property says that the sum of two numbers in a set also belongs to the same set. So, if we use real numbers a and b according to the property, their sum must also be real. So, back to the set in this question. It only has two numbers, 1 and -1. But do their sums belong to the same set as well? We just need to do some primary school addition to find out. Add 1 to itself. And what do you get? 2, which is not in the given set. How about 1 and -1? But 0 is not in the set either. And finally, what about the sum of -1 with itself? -2 doesn't belong to the set as well. Hence, this set does not have the closure property, at least in the case of addition. Maybe we will find some closure in our next example. So, what about multiplication then? Why don't we find out? Firstly, 1 times 1 is 1. Great, that's in the set. How about 1 times -1? We get -1, and yes, that's in the set too. Finally, let's try -1 and -1. We get +1, and hence proves this set follows the commutative property of multiplication. We can also say that this set is closed with respect to multiplication, since none of the products lie outside the given set. And with that, we have wrapped up the properties of real numbers. We'll meet complex numbers next. But hey, no worries because learning them won't be too complex.